Hi everyone, Dr. Hall again. We're going to talk about what's actually happening during the action potential now that we've reached threshold and decided to send one. And the action potential is all about ion channels. So we're going to talk about those in depth and then the different phases that we see of the action potential. So here we are in our outline. We are at 3C talking about ion. Oops, I messed up. So anyway, we have reached threshold. So I pressed the wrong button and then you can't go back when you're recording. All right. So we've reached thresholds, a combination of excitatory and inhibitory postsynaptic potentials, signals received from other neurons. We have changed the membrane potential, depolarized it up to -55 millivolts. And so the axon hillock has decided to send a signal. A couple of things about the action potential, which should be review from anatomy and physiology or human biology. Remember, the action potential is going to be a sequence of events and therefore a signal that travels down the axon. It starts in the axon hillock and moves down, sorry, I should go the same way as the slide, and moves down to the axon terminals. So it's going to happen again if the summation of the PSPs is such that you depolarize to -55. An action potential is an all or nothing phenomenon. There's no such thing as a big action potential or a little action potential. Either you do it or you don't. It's binary. It's a 1 or a 0. It's a yes or a no. You send it or you don't. And it only travels in one direction, again, from that axon hillock down to the axon terminals. So those are just a few things to keep in mind. All right, so what's going on with the ions? Because it's all about the ions. The first thing that happens when the axon hillock decides, right, so when we reach threshold, we reach that -55, is that -55 millivolts is enough of a specific change in the voltage that voltage-gated sodium channels open. And so when you get to -55, remember we talked about how some ion channels are voltage gated. So when you get to a certain voltage, they're going to open, and a certain other voltage, then they're going to close. So at -55, these sodium gates open. Now, if you remember when we talked about electrochemical gradient, sodium is very highly concentrated outside of the cell, so the chemical gradient favors moving inside of the cell, and the inside of the cell is negatively charged. Sodium is a positive ion. So the electrical gradient also favors sodium moving into the cell. So as soon as those channels open, sodium rushes inside the cell due to the electrochemical gradient. Now, that positive inrushing, or that inrushing of positively charged ions, is going to depolarize the next section of the axon. Its gates are going to open, sodium rushes in, and boom, 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 down the entire length of the axon. So when we're measuring the voltage, we can see here, let's see if I can not press the wrong button. Okay, so here we reach threshold right there. These sodium gates open, positively charged sodium ions rush into the cell, so the cell becomes more positive. It becomes less negative. It gets all the way to 0, and then it actually even overshoots. This up here is a positive charge relative to the outside of the cell. So that's a little bit of overshoot because so much sodium now is coming into the cell. And you might remember, what's the equilibrium potential for sodium? I think it's like +60 or something. So the sodium will keep going until you get to +60. It never gets that far, but we do overshoot and get above 0. So after that happens, these sodium channels are going to inactivate. So they're voltage gated in a way that regulates their opening, and then also once you depolarize to a certain extent, they inactivate. That little ball mechanism kind of covers up the pore, covers up the channel, and sodium can no longer cross the membrane. Now, if that was all that happened, then you would expect the membrane potential to just stay up here, right? Because now the sodium can't move anymore, so it would just stay there. But of course, it is not that simple. As you can see from the green line, we're going to have more voltage changes, and that's because our other ion is going to come on the scene. Potassium. So what happens is that reaching threshold triggers the opening of the sodium channels, but it also triggers the opening of these potassium channels. They're also voltage gated channels, and they're also going to open. Now, it just so happens they're a little bit slower to open than the sodium ones. So we don't see much movement of potassium until they're fully open, which is already at this stage of the action potential. So then our question becomes, which way is the potassium going to travel? So you have to think back to when we talked about electrochemical gradients and the Nernst equation and all that good stuff. I brought it back for you. So remember that the equilibrium potential for potassium is -91. There is such a concentration gradient with 150 inside the cell and only 5 millimoles outside of the cell that you have to make the inside of the cell -91, really negatively charged, to hold on to all those positively charged potassium ions so they don't go running out. So that's the equilibrium potential for potassium. Now remember, the resting potential where we were starting was -70. So even at -70, before we're doing any kind of action potential business, potassium is going to want to move out of the cell. We're depolarizing because sodium ions were rushing in. So now the potassium really, really, really want to get out of the cell. So when the voltage-gated potassium channels open, sodium is going to rush out of the cell. So now we have a positively charged ion leaving the cell. So that means that the cell becomes more negative again. So now we see this descending phase. We now see that the membrane potential of the cell is going back down to 0 and then back down, into the negatively charged territory. And in fact, it's even gonna like undershoot a little bit. It's gonna even get a little bit more negative than the -70. So that's called hyperpolarization. But this process of going back down to where you came from is called repolarization. After that all happens, we need to reset for the next time. So this is our first time actually talking about the sodium potassium ATP pump, or sodium potassium ATPase. So this is a membrane protein complex that spans the plasma membrane, and it's a pump. So it's going to use energy from ATP. It's going to split ATP into energy and ADP, so it can move the potassium ions back into the cell and the sodium ions back out of the cell. So it's going to go to work and pump everything back to its starting concentrations, back to lots of sodium outside of the cell and lots of potassium inside of the cell. And our membrane potential is going to go back to that -70 millivolts. Now, these little sodium potassium pumps are so busy and have so much work to do that they account for approximately 20 to 40% of all of our brain's energy use, right? So these guys are really busy. They have a lot of cleanup to do at the end of every action potential. So here's our summary of the different phases. So first of all, you get a bunch of EPSPs, excitatory postsynaptic potentials, signals from other neurons that change the membrane potential so that it depolarizes until it gets to approximately -55 and reaches threshold. Once it reaches threshold, those voltage-gated sodium channels are going to open, and sodium is going to rush into the cell, making the cell more positive and causing it to depolarize. So now our membrane potential goes up above 0, actually. Those sodium channels then inactivate. That little ball covers the pore. And now at this point, the potassium channels are open, and potassium really, really wants to leave the cell. So potassium is going to rush out of the cell, making the inside of the cell then more negative compared to outside the cell. We're going to undershoot a little bit, and we're going to get, we're going to undershoot a little bit and get even more negative than the -70. And then sodium potassium ATPase has to do all the cleanup, pump all the ions back, and get back to our starting phase. You want to say hi? This is Oliver. All right, so we've got the reaching the threshold. It's hard to do this with a cat on your lap. Then we have that rising phase where you see that the membrane potential is going up. It's becoming more positive as sodium rushes in. Then we have the falling phase as the potassium channels open and sodium rushes out. And then the action potential is done and the sodium potassium pump brings us back to baseline. This is everything in written out form. So again, you reach threshold, which is approximately -55. The voltage gated sodium channels open. As you can see, those are those purple ones. Sodium rushes in, we depolarize, then they deactivate. The potassium channels now are fully open, so potassium is going to rush out of the cell, and then we get all the way back negative. We undershoot a little bit, and then our sodium potassium ATP pump is going to move us back into our starting positions. And that's it for the action potential. In the next section, we'll talk about some characteristics such as the direction of travel, what regulates the direction of travel, the speed of travel, and the strength of a signal. So that'll come in 3D. See you then.